S- Hello everyone. This is Aditya, and I will be taking your deep learning session on. It is a continuation of the machine learning session, and I'm on behalf of GDSC and Hackslash. So let's start. Just give me a moment. Yeah. So, uh, the table of contents. So we will be starting with the introduction, and then we'll be going to analysis. And at this place, introduction and analysis, they both are basically a part of each other. That why we use deep learning, why we switched from machine learning to deep learning, and then we will jump into the programming part. So deep learning. Deep learning, it is basically a subset of machine learning, and why we shifted to deep learning instead of machine learning. So basically, we can say that because of a high computational power that deep learning takes, the uses of GPUs and other things, we have shifted to deep learning from machine learning. So, in layman terms, if I speak, I would say deep learning gives us a better capability in understanding the data set and giving us optimal results. So that's why we shifted to deep learning. So let's take an example. We have an image of a squirrel. This is a 1920 by 1280 size figure of a squirrel. So this is a color image, and it has them. So for the sake of this slides, for the sake of this video, we will take it as a dimension of 128 times 128. So basically, what do we mean by 128 times 128? This simply means that there are 128 horizontal rows and 128 horizontal columns. So basically, it's like a matrix of size 128 by 128 in which numbers are filled, and it has three channels. So basically it is a 3D matrix, something like this, where each row and column per channel is filled with numbers in the sense it ranges from 0 to 255. The RGB channel, the red, green, and blue channel. And superimposing those three matrices, we get the image, which is this squirrel image. And the most important thing we can notice here is the value which I said is between 0 and 255, but in the image you can say that you can see that it is between 0 and 1. It is like a probability. So basically what we do is we divide each and every cell by 255, so that gives us a flattened value, so it is easy to calculate. And as you can see that all 255 means full intensity, that's white. And if you put all zero, that is simply black. In the figure also you can see the less the value, the darker the corresponding cell is. So what I said in the previous channel, that's written here. So moving on. So what we do is we have to process the image. So for processing the image, the most important criteria is to input the values into something. So how are we going to input the values? So the most important thing here is we flatten them in a linear vector, in a row, I would say. So it is a one column and n row matrix where n is 128 times 128 times 3. So basically, it is the total information that that image has into one simple column vector. So why do we do this? Why do not we simply use a 3D element here? The reason is that it stores less space uh, as opposed to 3D. So in 3D, we will have to give it more space and more computing power than 1D. And once again, this is not a hard and fast rule. This is just what we follow. So moving on, how does a neural network work? So basically, each and every element, the x1, x2, x3, is multiplied by a weight. The weight is W1N. So what is this weight? This weight is basically the amount by which we will shift each and every pixel for the model to learn. And there is a bias, this B. So what does this B do? This B, what it simply does is it helps in making the model more accurate. Like if W does not correspond to good accuracy, this B manages that part. So this is just a simple neural network with one neuron. If I put it in another way, this is our column, then the value goes into one neural net, and then we have the output. So this is how it works at this place. And the sigmoid function, the this what is what you can see at the front. Sigmoid function is basically a probability function, which we will see later on. But what is the use of using a function here? The use of using a function here is to just flatten the values so that it does not increase exponentially, or the use of this is to put those values into a certain bracket, let's say between A and B, or from 0 to 100, and something like that. So moving on to the next slide. This is how a neural network work. So this is a fully connected layer where each neuron is connected to every another neuron in the next layer, and that neuron is connected to every another neuron in the next layer. So typically, the number of neurons in the input layer is determined by the dimensions of the input data. So in this part, we have 128 times 128 times 3 uh, rows, the input values. So if we will use that image as a training set, we will have 128 times 128 times 3 input neurons, these red dots which we are saying. And the numbers of output layers should be required, be set as required by the type of problem. So basically, if we have a data set where we have to find a squirrel versus a lion, then there will be two output. One, so completely for the squirrel, and second, which will be completely for the lion. And there will be a probability function. So if the image has a squirrel, it will say 1 in the squirrel, a number close to 1, like 0 0.8, 0 0.9, 0.95, something like that to the squirrel one. And to the lion, it will be like 0.1, 0.2, something. And moving on to the next page. Yeah, so weights and biases. We will deep dive into what are weights and biases. So you can read this page, what I explained earlier about weights and biases. That's all about for weights and biases. If you really have to go deep into that, you can study on your own. And on top of that, I would say that when you are studying something, refer to more than one paper or more than one document, because nothing, I mean, no one document has everything written in it. So let's move on to weights and biases. So, I mean, this has nothing which I have to explain. So let's move on. So, backpropagation. What is backpropagation? Let's come to the neural network image now. Yeah. So let's say we gave input. It passed through the hidden layer and went to the output. So what will the model do next? So the model will compare this particular output with the feeded data, that did the pixel which I got here. So it will make a image here. Image not in the sense exactly like that, but the color will be. You can say that the input image will be superimposed and blurred, and that will come as the output. So in one simple layman terms, so this will compare it with the input data, and it will see that okay, so at this point my pixel value was 0.5, but here the pixel value is 0.6. So let's compare it with the neighboring values, and that is what backpropagation. So the output will go to the hidden layer will go to the previous hidden layer, and so on. So hidden layer basically is, I would say, hidden layers are used to make the model learn more deeper values or more intricate values that the image has. So yeah, that's all about backpropagation. And backpropagation also adjusts the weights and minimizes the overall loss and error. So it adjusts both weights and biases. I will show you how. So as a forward pass, I told what it was. Back propagation, I told what it was. Weight update, I told you what it was. Now let's come to loss computation. The loss or error between predictions and actual targets is calculated, like how they are calculated. So the weights in the neural networks are updated iteratively to minimize the loss function. So how do we update the weights? So basically, we can say that the weights are updated like every batch or every pass. So you can set it in the code. I will show you how they are done. So every forward pass is followed by a back propagation. Okay, so to update the loss, to minimize the loss with respect to the weights, the learning rate determines the step size of the update. So you can visualize this as, let's say this is our data set. This is the learning rate, not the learning rate. This is the what I would say is the loss, the loss. So what it does is we have to minimize the loss. So it's obvious that the minimum part is here. So let's say at first our model is here. It's predicting at this place. So let's say we put a what was the uh, gradient descent of the respect to the loss function. The yeah, the learning rate. Yeah. So the learning rate, if it is large, the model will shift from here to this point. Then from this point, it will go something like this. But if the learning rate is lower, what the model will do, it will go very smoothly to this place. And then it will go again to this place. Then it will go again from this to this place. Then it will go to this place. Then it will move up. It will see, okay, so the loss is getting increased, so it will go backward. As it is evident that if the learning rate is very, very small, it will take very huge amount of time and very high huge amount of calculations to come to the bottom. So we put a learning rate in a way that is very convenient, so that the model reaches the minimal amount of loss in a definite amount of time. So basically, in general, for most of the cases, alpha is defined by the learning rate, and if we put alpha as 0.01, it works. So alpha is equal to 0.01 works almost all the time. So if we use sigmoid as an activation function, it is easy to do the differentiation if loss has log term is it. So this is very obvious that how is sigmoid defined? Let's first see that. So sigmoid is basically 1 upon 1 plus e to the power negative of x. So yeah, basically there is an term of e, which is the Euler's constant. The log value will make it easy for it to differentiate, because the differentiation of e is always e, and differentiation of log of y dash is equal to y upon y double dash. I mean, this is not a differentiation. These are two different values. You should not confuse between them. Y is the actual ground truth value, and y dash is the predicted value. We can, for the sake of this paper, for this slide, we will call this as y hat, not as y dash. So this is y hat dash. If we differentiate, this particular term will be y hat upon y hat dash. So that is why we use a log in we use a log value to calculate to calculate loss when we use a sigmoid function. So sigmoid function, as I told you, this shows probability. What it does is sigmoid function prints the output between 0 and 1. Whatever you input to the sigmoid function, the value will be between 0 and 1. So when x is large, very large, it will shift to 1. When x is 0, it will shift to 1 by 2, that is 0.5. When x is negative, it will shift to 0. Excuse me. So that's what it does. So if we see, this is this loss value, where does this come? It comes from maximum likelihood estimation. This is a part of statistics. So if you just Google it out, what is maximum likelihood estimation? It is basically a graph which you might have seen in your 11th and 12th in gas and kinetics chapter, that Maxwell distribution curve. I mean, it is nearly equal. I mean, the graph looks like that. If you see it, if you Google it out, maximum likelihood estimation. I'm not really sure if that's the case or not. Just Google it out and read about it. So this loss value comes from maximum likelihood estimation. So how are weights and biases updated? So as I said, weights and biases, they have to be such that the loss is minimized. Okay, the loss is minimized. So this is the gradient descent, which I told you here. This is a weight, this is the loss, the learning rate, and the descent, what's happening. This is the gradient descent algorithm, what occurs there. This is not in two dimension, it is in many dimensions depending upon the feature and the model which you are using. So that's how weights and biases is updated. So what is ReLU? This is a linear rectified unit. What does it mean? So ReLU is basically something like this. Hmm. So for all values negative, it shifts them to 0, and it prints the positive value as they are. So does it print the positive value as they are? It depends what your equation is. If this side is y is equal to x, it will do it. If it's something other than this, it will do that. So why do we use, so why have I mentioned sigmoid and ReLU here? There are many activation functions like tan, h, and all and all. So basically, ReLU is used because if we use too many sigmoid functions, as you can see, that the value will get that the delta value will get very low. When I, let's say, use a sigmoid of x, and when I use a sigmoid of x, like there are two functions, one inside the another, the value will be very less. The shift in value will be very less. Like sigmoid of 10 and sigmoid of 11 will have very less differences. So to help the updation of weights and bias in a very neat manner, this is used. So I mean, relu is used. So what we do is we use an input layer, then we use relu, then we use a hidden layer, we use relu, we use hidden layer, we use relu, and on the last output layer only we use the sigmoid function, which gives us the probability. So we will move on to programming part. So language. So machine learning can have, I would say, can be used in various programming languages. So I would say that when you use machine learning, I mean, when you use a programming language to write the code, what you basically do is you take a programming language of your choice. So there are many languages. So Python is most widely prepared for writing deep learning, machine learning code due to its simplicity and very extensive libraries. So we will be using Python for the sake of this video, and we will be using an environment, Google Colab. So Google Colab basically gives us a cloud service where we can use machine learning, where we can write machine learning codes. And okay, so let's move on to code. So I would open Google Collaboratory. All right, so this is the Google Colab environment. So first we will connect it with a runtime unit. We will use the graphics processing unit because it's fast. It's faster than CPU for a numerical calculation. So moving on. Okay, so what we learned in this part was sigmoid function. So at first, let's see how a sigmoid function looks like using code. So we will define a sigmoid function, and let's say the value is equal to 1 upon 1 plus torch dot exp x. So this will give us an error at present. It did not. Okay. Torch is not defined. X is equal to 23. Mm, value. Okay. So it says that value is not defined. Let's so basically what I did at this place is I defined a sigmoid function in Python. The value is equal to 1 upon 1 plus torch dot exp x. I have to return it to return value x is equal to sigmoid of let's say 32. So this value gives an error. Yeah. So why did it gave us an error? Because we are using a torch function for calculating the exponential of x. This will be negative of x because here it is 1 upon 1 plus e raised to the power negative of x. And let's import the torch library. Torch library is basically the PyTorch library. It is used to do multiple machine learning and deep learning things. So this should give us some value. Hmm, x dot okay, uh, torch dot value. Uh, no wait. Okay, so torch is a library used to do deep learning, and at this place, we will be writing our code to plot that graph. So basically, what Torch does is it takes data in tensors, which is a torch tensor or a PyTorch tensor. So we will be inputting the value in form of a tensor. So y is equal to sigmoid of x. This should run. Yeah. So this is it. And how do we plot it? So for plotting, we use a library, matplotlib.pyplot. So matplotlib is a library which helps us in plotting in a easy manner. So we will write some code for plotting. And plt dot, it should be figure, and plt dot pyplot x comma y comma minus r len width is equal to line width. It should be let's say positive of 2. That's in pixel. Plt dot mm, plt type layout plt dot show. Okay, so this should be good enough for us to plot our figure. Mm, module map no attribute pyplot. Okay, so here it will be directly plot. Yeah. Okay, so as you can see, this is our sigmoid function which we did plot using Python and using some libraries, where the more negative it reaches 0, at 0 it is 0.5, and at infinity it will reach 1. So at this place, if you will see, the important part is this part, which takes value as tensors, and we did input as tensors, which is line space negative of 6 6 to 100, like in 100 divisions. Okay. Yeah. So from minus 6 to 6, this will go in 100 subparts, like 100 different values. And so come back, we can see at this place that what I started with was an image of a squirrel. So let's do some calculations on this image. So for that, I will import the image which I have at this place as a small animal. So As you can see, the image of that small animal is loading. So let's wait and okay, it's done. So first we will define the image path, that where the image is. So it will be like small animal dot jpg. Okay, it's done. So right now what I am going to do is uh, convert this into numbers and then I will show you. So this will not work because MPIMG is not defined. So we will be inputting the necessary libraries for that. So import numpy as np. This will be for that, and then import matplotlib dot image as mpimg. So matplotlib also has an image reading function. So this place is reads the image, and then we will print the image. Okay. So as you can see that the image which I told you has dimensions 1280 by 1920. So let's further do some analysis and add grids here. plt.axis on, and then plt.grid on, and then plt.show. So as you can see that we have added some grids at this place, and for further analysis, what we are going to do, these grids will be important. So let's move on. Let's see the shape of that image dot shape. The shape is 1280 by 1920, and it has three color channels, as I have said in that slide. So moving on, we will see that let's do something. IMG is equal to IMG by 255. So what I did here was I flattened the values which were between 0 and 255 to a probability like number between 0 and 1. So let's separate the image into its color channels. So from that, for that we will be using another library which is PIL, and we have the image path, and then we will read that image dot read. It's not image dot open, and then it is irg path. So what it did, it okay, it read the image, the PIL library, so it is stored. Now we will say that the three color channels, I will split it. So now I will do something like figure axis plt dot subplots 1,3 big size is equal to 12, so, and now what I will do is I'll plot it. So in these three images, you will be getting this the color channels of the squirrel. So for that, I would say that we select the first axis, and we print there the red mapping, which we will name as CMAP is equal to red. Access AXES. What's the value? Red is not a value. Okay, okay. So it's a spelling error. Okay. Hmm. Okay, now we will plot it. Uh, plt dot show. Okay. What's happening? Just a minute. Plt dot. The figure size is something like this, and did I do something wrong? Just wait a moment. I will be seeing this. Access plt dot show subplots img path. This is clear image dot open img dot split subplots. I guess everything is correct, but access spelling fig access im show r cmap reds tight layout show. Just wait a moment. Plt dot show. What's happening? Mm, it should print things, I guess. But why is it not doing anything like cmap access subplots plt dot tight layout? Okay, so access dot I am sure everything is correct according to me, but let's do something. Let's do it as 1 and 2. This is green, this is blue. Okay, so this thing is not. Okay. Plt dot show plt 012 dot im show. We did take it as rgb img dot split at this place. Uh, okay, yeah. So I do not know what the problem was, but in different cells, this was not reading the value. So at this place, as you can see that we have separated this squirrel image into its three color channels, the red, green, and blue. So moving on, as you can see that the black part, the eye, at this place, every value should be 0. So that should be white, white, and white. And the image is separated into three color channels. And if I do something like I plot the values for I in range 5, for j in range, for k in range. So if we do it something like the print the values at this place, what we will get is So if I do something like I plus 1, j plus 1, and k plus 1. So what I'm doing is I'm printing the values. It will show us how good that value is. Print the image. So it will be something like this. IMG 0. This will be I. Then I'll have a J. Then I'll have a 0. Okay. So if we print this values, what we will get is int object is not callable. Okay, so why is that? Okay, there some should be a multiply sign. At this place, what the problem is, JPG image file is not subscriptable. So for that, I would say is let's use this once more at this place. So the image path is this one, and we will read that image. The moment we read the image, things should go. What I have to do is img is equal to img by 255. Okay, so as you can see that I have written all the color channels. So the third color channel is the blue one. So at this place, the top part, from here we are noticing the value, and from this part in the y-axis. So as you can see that this part is green and this part is green. So green means it should have green and red only, but as there is a tint of brown in this place but no blue. So as we can see that blue is very less in the third color channel, as it is evident that blue at this place is very less. So that's all. For 0 to 25, we will see that the blue color channel has very less values. So that's all about the image thing, and now we will be moving into minced dataset. So what is minced dataset? Minced dataset is basically numbers written from 0 to 1, 2, 3, 4, 5 to 9, handwritten digit classification. So for handwritten digit classification, we use the minced dataset. So I'll be just doing a walkthrough. So TensorFlow, we will be using TensorFlow. TensorFlow is also a library like PyTorch, which helps us in doing machine learning. Uh, we will do import. So matplotlib is already imported. We do not need numpy is also done. Import random. I'll show you why I'm doing all this stuffs. So first what we will do is we will call the minced dataset. So how do we call the minced dataset in TensorFlow? So am I visible to you guys? Like, I guess there is a problem. Okay, so everything is all good. So how do we call that? So it's like MNIST is equal to TensorFlow dot keras dot dataset dot minced. So keras is an API on top of TensorFlow, so it helps you to do machine learning things a little bit easier. Okay, so has no attribute dataset. Okay, so it will be data sets. Yeah. So we will split it into training images and train label and on test image and text test labels. Okay, so as you can see, this thing is unmatched. Okay, so now our data set is downloaded from the TensorFlow library and it is ready for use. So as I have said, we flatten the values. So we flatten the values. Trained images is equal to numpy dot expand dimension and trained images axis is equal to negative of 1. What it does, it adds another axis. We will look into later why we did it. Dot the type we will set as let's say float, float 32 or something. Okay, so this is done, and we will do the same for the test images. This is how we do it. It will be the same, and since we converted the train images into numpy arrays, we will use this. We will convert this into numpy arrays as well. Train label dot a as type. This will be np.int64. So train labels and test labels, train labels. Okay, so let's copy paste if it's not defined. I don't know what the problem was, but test label, train label, uh, train labels. Okay, so what we did as of now is we converted everything into a numpy array. So now we will just look into how the data set looks like. All right, so let's do that. The figure size should be like 10 by 10, not so big, not so small. And so we will write a variable named random indices. So what it does is it generates random numbers for us between 60,000 into 36. So between 1 to 60,000 it generates. So what minced data set is, it's like it is a data set of 0, 1, 2, 3, continue till 9, and it is separated into 60,000 images training and 10,000 images on testing. So a total of 70,000 images. So we will be looking into the first 60,000, which is the training images. So if we do, so let's print it for I in a range 36, plt dot subplot 6 comma 6 comma I plus 1, which will be the number like 1 2 3 4 5 6 to 36, and plt dot x ticks, which will carry the value what to fill at this place. Then we will have the y ticks. Then we do not want any grid, and the image indices uh, should be equal to random indices per value, and on top of this, if we will plot it, I am show np.squeeze. I guess the spelling is correct. Squeeze. Yeah. So what we will print is the training images, and image int cmap is equal to plt.cm dot. So it is a binary text, not binary. It is a grayscale image. I mean black and white, whatever you call that. It is like that. The means data set. So I am age image indices in binary output, and the X label will be our train label. So this will be like image indices. So this should be good enough. Yeah. So this is how the minced data set looks like. So we did sample out some random numbers from it, and we can see that how the data set looks like. It is a handwritten classification, a handwritten digit classification. And so we will train our model right now. So we will use the libraries sequential, sequentil, and what we will do is we will define, so flatten. So we flatten the image into one column vector, so the data set is very good. So the data which it takes is less. So input shape is equal to 28 times 28. It is a one channel only, so we define it, and then we will write like a dense layer of 728 inputs. The activation is a relu, and we will write, let's say, another dense layer of 10 output with activation as softmax. Okay, so if we run it now, this will not work. This will not work because we did not define that what is sequential, what is flattened, what is dense. We have what is activation function, what's the input shape, like how do you process the input shape. So this will not work. This will show us an error. So for this, we will import some libraries which will help us in running the code. So import TensorFlow SDF. Then from the Keras API, the layers, we import flatten, dense, and from TensorFlow dot keras dot models, we import sequential, this thing. So we imported everything, I guess. Yes. So if we run it now, this should work fine. So right now, this showed some error. It did not TensorFlow. Okay, so everything works good. So this should work. Okay, so our model is defined, which is a flattened layer. There will be only two, I guess two should not be present. I will add some more. So let's say this is 428 and this is, let's say 64. This, I mean, these two are hidden layers. Hidden because, as I've told you, hidden layers helps the model to get more information about what you did input into the image. I mean, to get more information about the image. So right now we will compile it, and it will show optimizer as Adam, and the loss should be sparse categorical entropy. It will be cross entropy, CROSS. Uh, Gross entropy, and the matrices will be accuracy. So the model has to increase the accuracy. So this should work, I guess. Hmm, okay. So what's the problem here is uh, invalid keyword argument in compile matrices. Okay, the spelling is wrong. Matrices. Okay, this is right. Matrix. Okay. Sparse categorical cross entropy. Cross entropy. I do not know why there is a red line. Model.compile the Adam optimizer. The loss will be sparse categorical cross entropy sparse, and the prediction should be on the accuracy point. Uh, Keras.layers TensorFlow Keras, but models import sequence. Okay, let's do something. Let's then see what happens. So we will do model.fit and train label, train images, then train labels. The batch size should be equal to, let's say, 64. The epochs will be equal to 10, and then we will run the model. So it is running. Let's see what happens. Okay, so it's doing pretty good. Let's wait, it's just completing. Okay, so it's done. So if we evaluate the model, the test, uh, make sure all the arrays contain the same number of sample. Okay, so test images, test labels, test loss, comma, test accuracy, model dot evaluate. test images, test labels. What's the problem? Okay, so y size is 10,000. Test test labels. Okay, so I guess I did little bit error at this place, I guess. Hmm, test images, train. Okay, okay, okay. Yeah, at this place I did wrong. Test images, train labels, test label. Okay, so I have to run the code again. So let's run the code again. This time I guess it should work fine. Yeah, everything is all good. So let's wait until the model runs completely. So as you can see that the accuracy is getting up and down, up and down. So what's happening is after every back propagation, when the weights and biases are updated, the accuracy factor is also affected by that. So right now, I guess things should work and we should get something like uh, test loss, test images and test labels. Test images has test images and test labels has test labels. Something like train labels then. Hmm. I do not know why the problem is here, but up until now you can see that the model is 99.50. So the accuracy is 99.50. Actually, this is only on the training set. So until we do not evaluate the model on the test set, we do not really know. But the accuracy will be nearly this, uh, nearly. So the model will have a near accuracy of this thing. So this is what it is to do deep learning and stuffs like image processing, as you can see. That's all about today's session, and thank you all for joining.